Good morning. Yeah, we can get
Good,
started.
good morning. Good morning, please. So, very nice that already through these question answer, all of you could recollect whatever was spoken of in our last meeting, and that was the ideas about what we nowadays call atoms. Earlier, people, that is, from the time of John Dalton, people thought that an atom cannot be divided, and atoms of different substances are different. That part is definitely correct. But atoms of different of any substance uh, cannot be further divided into smaller parts, and that is why atoms were called fundamental particles. So this finally got a completely setback when in 1897 Sir J.J. Thomson, he discovered the electron. And what he found was that what actually he measured was that when you take a gas, and this gas you put under high voltage and many other things he did, and in this column of gas, it is like say a cylinder. You have an electrode, that is a plate which you charge positively, another you charge negatively. Then between these two, there looks to be some rays were passing, some things were passing. Then people put a magnetic field, and on putting the magnetic field, they could find that these could be bent, that this track of these, whatever was passing, they could be bent. And once they knew that with a magnetic field, things can be bent, it was very clear that these must be charged particles. And by bending with the magnetic field, what Sir J.J. Thomson did, he tried to find what we call E by M ratio. That is their charge divided by their mass. This is called E by M ratio. What he found that if no matter what material or what gas we fill these tubes with, whether it's hydrogen, whether it's helium, whether it's lithium, no matter whatever uh, substance we fill it with, the result is the same. The result of E by M ratio is the same. And these are all negatively charged particles. These are negatively charged particles. E by M ratio is the same. Now, last time somebody spoke to us about ions, ionic materials. Now, what are ions of an atom? Ion is that if you take an atom, and people did not know about electron in those days, but it leaves, if an electron is taken out, a positive charge will be left, and those are called ions. I-O-N, ions. Those are called ions. And the name, it is a very strange where the name comes from. Name comes from a group of Greeks, and those Greeks were called the Ionians. And these Greek people were great travelers. So since the ions, it was found to move about, so these positively charged particles, they were called ions because they move around all the time. So therefore, the charge by mass of ions had been calculated, but here he found that that there were some negative, and they were all positive, all these ions were positive. But here he found that there were some particles which are negatively charged. How did he find negatively charged? When on put an magnetic field, it bent in a certain direction. If it were positively charged, they would have bent in the opposite direction. So that's the way they understood that these must be uh, negatively charged particles. But what surprised most was it is not only negatively charged, but if you see the E by M ratio, it is the same ratio that comes from no matter whatever material you fill or whatever gas you fill the gas the tube with. And this E by M ratio was a very high value, was a very high value. Whatever it was for hydrogen, not, yeah, hydrogen ions, because by that time hydrogen ions E by M had been found. This is about 1,830 times more. 1,830 times more than the E by M value that we would get for hydrogen. So what could it be? The only conclusion that he could get is that given that the charge is fixed, E by M ratio, you understand? So mass comes in the denominator. So this is a particle about 1,837 times lighter than hydrogen ion. 1,838 times lighter than hydrogen ion, and that is why the E by M ratio was 1,830 times more than what we know it for hydrogen. So if it be so, then its mass is so low. Its mass must be very low. Of course, its mass he could not get accurately because he could not measure the mass separately. He could get only E by M. So if he knew E, that is electrical charge, value of the electrical charge, then he would have got M. And there was no other separate method to measure this M. Now the value of the charge was measured very accurately by about 1912. That is 15 years after the discovery of the electron. 15 years later, by another very classic experiment, it is uh, uh, Milliken's oil drop experiment. Milliken did the experiment, and this this charge was found of the electron. And once the charge is found, and E by M is known, so you substitute the value of E, then the mass would come out. And the
I
mass
had a
was found.
question, Professor. Sorry.
Yes.
What were you saying is 1,837 times more than the E by M of hydrogen?
The E by M value that it was found for this electron
Okay.
was 1,837 times more. So therefore the conclusion is, if their charges are the same, now you see, as I said, if, because whether the charges are the same, we still did not know. If their charges were the same, then the mass has to be 1,837 times lower. Okay, it has to be that. Now, what is the actual mass? In order to know, we had to know the charge. And the experiments to find the charge finally got us a very accurate value for the charge of the electron. And that was done what is called the famous Milliken oil drop experiments. We will not go into that. So therefore, the charge was found, mass was found, and this is the lightest mass that is known. This is the smallest charge that is known, and this is also the lightest mass that is known. And all our understanding of our quantum world, one of the fundamental points, basic points that has to be kept in mind, that electron is the lightest particle, this is its charge, and this is its mass. And this is one of the basic issues that we have with us in the quantum world. Second point that uh, we have told is that by various means, and one of them is by measuring the viscosity, diffusion constants, etc., etc., the sizes of atoms and molecules were found. And hydrogen atoms size, as we said a little while ago, it's about 0.5 into 10 to the power minus 8 centimeters. 0.5 or 0.52, something like that. So it is a very small particles, 10 to the power minus 8 centimeters, very, very small length scale. Now question is, what is a time scale? Now about the time scale, people could guess. The time scales of motion inside the atom should be of the order of 10 to the power, or rather 1 upon 10 to the power 15 seconds. That is 10, roughly 10 to the of the order of, I'm talking of the exact, of the order of 10 to the power minus 15 seconds. That is the time scale. All right, time scales. Question is, how did we get that guess? That guess was found in a very different way, because by that time we had understood the ideas of spectroscopy, which sometimes I had mentioned that if an atom, if you shine light on an atom, it will absorb the atom, absorb radiation, or it will emit radiation if it is highly heated. If it is highly heated, it will emit radiation. If it be, if you shine light on it and keep it cool, it will absorb radiation. And people could measure the wavelength of this radiation. There are various techniques, and by these techniques of spectroscopy, they could find. And this radiation, when they found, their wavelengths also they understood, they were roughly between 4,000 to 6,500 angstroms. Angstrom unit, I told you, is 10 to the power minus 8 centimeters. So if this is the wavelength, then what is the frequency? Now, speed of any wave, including light, is the speed of light would be
300,000 meters per second.
in vacuum, that's the number, but it should be equal to the frequency multiplied by the wavelength. It should be the frequency multiplied by the wavelength. Now, frequency we found from all these atomic issues, that let us take it as 6,000 angstroms. That is 6,000 multiplied by 10 to the power 8, 10 to the minus 8. So which became 6 into 10 to the power minus 5, correct?
Mm-hmm.
It becomes 6 into 10 to the power minus 5. So therefore, C, speed of light, should be frequency multiplied by 6 into 10 to the power minus 5. Okay? 6 into 10 to the power minus 5. Now you divide. So you'll find the frequency is equal to 3 into 10 to the power 10 divided by 6 into 10 to the power minus 5. It becomes roughly 0.5 into 10 to the power 15. Okay? 0.5 into 10 to the power 15. That is the, in the visible range of light, the frequencies are of that order. 10 to the power 14 to 10 to the power 15, that is the frequency. So what should be the time scales? Time scales should be 1 upon frequencies. And therefore time scales you find is roughly, yes, roughly the same as 10 to the power minus 15, minus 14 seconds. So therefore, since light can be absorbed or emitted by these atoms, and since light carries this level of time scales, I'm talking visible light, since light is carrying some uh, this kind of time scales, so time scale of motion inside the atoms must also be of that order. That is
Like
10 to the power minus 14 to 10 to the power minus 15. This level, 10 to the power minus 14 to 10 to the power minus 15 seconds. These have to be the nature or the order of magnitude or the scale of the time scales that we have in the dynamics inside the atom. This became a big problem to understand because we have never come across such huge time scales yes, such fast time scales. We have never come across such uh, time scales. So how to understand them? How to understand? That was the problem that we had. And in order to understand that, people did not know for a very long time as to what should be done. One of the questions that came up, and that is that we already know of an ion, we already know of the electron, and we know that the atom is electrically neutral. So both the positive charge and the negative charge must be in the atom. But how they are distributed? They're all mixed up together, that there is a certain cell in which the positive charge lives, there's another cell in which the negative charge lives, and they're all uniformly distributed. That was the one possibility that people were thinking of. And it was in order to verify this kind of things that Ernest Rutherford, he did that classic gold foil experiment, and there he bombarded it with positively charged particles. That those were alpha particles, and uh, these alpha particles had they're positively charged, but they had double the amount of charge than an electron. If electron charge is E, then we would say that the alpha particle charge is 2e. Now, as it was said before we started this discussion, that all the positive charges inside the atom would repel these alpha particles. Now, if they were uniformly distributed, then one positive charge will repel the alpha particle a little bit, next one a little bit more, or another one a little bit, and all these tiny amounts have to be added up. And if you add up all these tiny deflections, then the repulsion would be given as a certain kind of scattering angle. So this was to be expected. But when the experiment was done, they found that no, most of them had very little deflections, but there were some which were 1 in 100,000 or so, which were deflected by 90 degrees or more. If these charges were all uniformly distributed within the atom, then we would not expect such high deflections at all. But the very fact that though small, but there were some which were deflected by such large angles, it showed to Rutherford that yes, the charge inside the atom is not uniformly distributed. It is not at all. Now you see, comes the mark I would say, of a genius. Any other person would have said, oh, 1 in 100,000, it is too small. You understand? 1 in 100,000, it is too small. Let us ignore that. Okay? But not a person who has the level of understanding that Lord Rutherford had. And he asked the question that even though small numbers in proportion, why are they getting deflected at all by such angles? Fact was not whether they were small in number, but they were there at all. And its only conclusion could be that this is possible only if the charged particles are concentrated at a very, very small region. And this region is called the nucleus. All the positive charge inside the atom resides inside the nucleus. And so you can understand what happens, that most of the alpha particles which go far away from the nucleus, they hardly get deflected. They hardly get deflected. But the ones which approach the nucleus too close, they will have a very strong deflection. And this deflection can be more than 90 degrees. And sometimes some of them can be completely rebound backwards. That is, come back in the direction in which they were coming. This conclusion from the experiment was inescapable. You could not come to any other conclusion. And that is how the discovery of the electron, of the nucleus in an atom came about. Now, nucleus, as we say, we understand they are positive charges. So people try to find out, again, as I said, the charge versus mass of the nuclei. They tried to find out, they also tried to find out that they found that the mass of the nucleus was, uh, yes, mass of, so, and not only that, they had also found out the mass of the hydrogen atom, not hydrogen, hydrogen atom, hydrogen ion. So there was a, people tried to fix that, okay, hydrogen ion is the fundamental positive charge, and they named it a proton. A hydrogen ion there's no positive charge, or there's no particle with a lower positive charge, and this was called the proton. So when they tried to find out the mass of the nucleus of different atoms, they found that these atoms, except for hydrogen, were actually heavier than what if I said that if they are composed of proton. For example, hydrogen has only one proton. Now helium, we knew, we could find out its charge is 2, plus 2. Helium ion's charge is plus 2. So suppose I say that yes, helium ion's mass is therefore, I'm sorry, helium ion's mass is therefore 2 protons. We found that it is actually heavier than what we would get if we assume that these were only 2 protons. So similarly, if you get to carbon, you know, carbon ion's charge is 6. But if you try to find out what is the mass of the carbon ion, we found it is heavier, about double the mass of 6 protons. So therefore, apart from the nucleus, apart from the protons, inside the nucleus, there should be something else which does not have any charge, and it is neutral. This was discovered only in 1931-32. That you see the delay between the discovery of the electron, 1897 to 1932, which means about 35 years. So science is not a very direct thing. That is, you find today something and tomorrow the next discovery comes. It never happens like that. Science has to progress. People have to understand more and more, in just like the way you learn in school. First, you learn your alphabets. Then, from the alphabets, you make a word. And from the word, you make a sentence. From the sentence, you make a paragraph. The paragraph, you make a story. And if you continue like that, and if you go on practicing, maybe some of you will write a book. So same thing happens in science. We have to go step by step, and there is no shortcut. And that is why, since there is no shortcut, sometimes discoveries take such a long time. 1897 was the discovery of the electron. 1909, I think, was the, or 1911, something around that time, was the discovery of the nucleus. And after that discovery of the nucleus, we had to wait about 20, 21 years to finally discover that there is, yes, there is a neutral particle inside the nucleus, and that we named as proton. I'm sorry, as neutron. That was called the neutron. So roughly we can say, or rather fairly with very great level of confidence and accuracy, that we can say that the atom consists of a nucleus. The nucleus has positively charged protons and neutral particles, which are called neutrons. Then comes the question, where are these electrons then? Where should it be? The electrons obviously cannot be inside the nucleus. They have to be outside, because we have already discovered that there is a concentrated positive charge, and that is the nucleus. So all the electrons must be outside the nucleus. And if they are, how they are moving, that's one point. And secondly, if whatever, so only possibility was they must be moving in planetary type orbits, which we already know. As you understand, as you might have come across, and we have said before, that when you take a planetary motion, that is a planet moving around the sun, we know that its motion has to be fairly elliptic kind, let us not bother, but they go in orbits which keep moving so that it comes back to its same point. For the case of Earth, it is roughly in 365 days. So it is a periodic motion. That is, it begins, comes back repeatedly to the same point. And while coming back, it maintains the same length of time or same time interval. It comes back in every 365 days. So what should happen in an atom? Since there is a positive charge and electrons are negative charge, and they have to remain separated, because otherwise we cannot see electrons or protons. They have to remain separated. The electron will always be attracted towards a positive charge. So it should fall inside the positive charge, but its fall can be stopped only if it is moving around with a certain speed. What should that speed be to stop its falling? And what necessarily should the time scale of its orbit be? These are the questions that would automatically come up when we talk of the time scales or the dynamics inside. The dynamics, from the point of view of spectroscopy, had given us a time scale. And that time scale is roughly 10 to the power minus 14 to 10 to the power minus 15 seconds. Now, can the electron move with that kind of a frequency inside the atom? Because why are we connecting all these? We are connecting because we have seen that light can be absorbed or emitted. And light cannot be absorbed or emitted in free space. Light, for its absorption or emission, it needs matter. And that matter is composed of atoms. And that atom now we find. So atoms have to do something with this process of emission and absorption. And that has to do, and now that we know that the atom consists of the nucleus and of electrons, then the motion of the electrons around the nucleus must have to do something to do with this absorption and emission process. So what could that be? We already know, as you have already come across in your school, that there is something called conservation of energy. That energy can neither be created nor can be destroyed. It can be redistributed. Redistributed in the following sense: light is coming from somewhere, it shines. Yes, same with mass, correct? Same with mass, same with momentum. So light comes and it can give part of its energy to someone, and rest of it may move away. So therefore, very clear, since we know that no matter what happens, there has to be a conservation of energy. The light energy which it comes must give its energy to the electron in the atom, so that in such a process, light will get absorbed. And again, an electron will gain some energy. And if light is to be emitted, electron should lose energy and give it out in the form of light. So this is the process of the interaction of energy between the electron and the and light that goes on. So electron and light have to go on in this kind of exchange of energy between them. But while doing this exchange, the conservation of energy must remain. And so this was one of the issues. And it is very clear that if such a thing has to take place, then electrons in an atom has to have in their motion a time scales of the order of 10 to the power 14, or rather 10 to the power minus 14 to 10 to the power minus 15. So how was it possible? There came a big problem. The problem was very serious, and that has to not to do with atomic science, but that has to do with another area, and that was with electromagnetism. So as I said, that the story of atomic science, or the story of the science in the 20th century, cannot be described as a single one-dimensional forward motion. What these days you will say, I think in films and all those movies that you see, that you pause. In movies, there's something called a flashback. That is, something has happened. Now you go back, try to remember what had happened, then move ahead. Nowadays, when you see videos or earlier or videos, etc., we say that yes, let us press the pause button. And after pausing, you have to go back and see, let us see it again. Now here also, not only we should see, but we should see from a different point. And that point right now has nothing to do with atoms. And that has to do with the electricity and magnetism. The major ideas of electricity and magnetism, they emerged from around 1800 onwards. And all that was to be discovered in terms of fundamental questions of electricity and magnetism were discovered by 1832. In about 32 years, it was all discovered. And by 1864, The last great discovery was by Michael Faraday, Michael Faraday, and from England, and Henry from the United States. So, what are the basic things about electricity and magnetism? That charges interact with you. There are two kinds of charges, positive and negative. In gravitation, we never had a negative mass. We always have a positive mass. So here there are positive and negative. Light charges repel. That is, two negative charges will always repel. Two positive charges will always repel. And unlike charges, they always attract. Okay? And this attraction also goes as product of the two charges divided by their distance to the power 2. This is called the inverse square law. There is an inverse square law in gravitation also. And that inverse square law says the two objects always attract each other, and this attraction is proportional to product of their masses divided by the distance square. Now, structure of the two laws may look to be the same, but there's a very important difference. That gravitational forces are always attractive. There's no repulsive gravitational force. There's no repulsion in gravity. But in electricity and magnetism, you can have both attraction and repulsion. both can be there. This is one part. Second part is, if the charges are not moving, they cannot create any magnetic field. In order to create a magnetic field, charges have to move. This is again. And there was a final important issue. Yes, inverse square law means that is the force between these two objects go as 1 upon distance to the power 2. Now, distance to the power 2 is square, distance square. And since we have put it 1 upon that distance square, it is called an inverse square. 1 upon distance square. It is there in gravity. Yes, product of the charges divided by d to the power 2. This is called the inverse square law. Now, in gravity, we know that there are inverse square laws. And because of this inverse square law, they move around orbits, which we had told of Kepler. So one person who immediately said that there should be the electron motion in orbits in the atom also, the man's name was Niels Bohr. In 1913, he said there are these planetary orbits, but it cannot have all kinds of planetary orbits. Planetary orbits are circular. That's one. Second thing is that they are possible to have planetary orbits only if these orbits satisfy a condition, and that condition is that mass of the electron. Planetary orbits can be elliptical. The most general things are elliptical, but you see, circular is a very special case of elliptical. That is, circular is a case where it's what we call the ellipticity. That is, its oblongness is 0. Okay, so circle is a very special case of an elliptic. That is, in ellipse we have a major axis length and a minor axis, and if they are different, we call it an ellipse, and if these two become equal, we call it a circle. A circle is a very special case of an ellipse. So these have to be circular orbits, but not all possible circular, not any circular orbit is possible. And there he gave a condition, and that condition is the following. That is, measure the circumference of this orbit Suppose the orbit has a radius r, then its total circumference will be 2 pi into r. Okay, 2 pi into r. Multiply it by the momentum of its orbital motion, and that momentum should be mass of the electron multiplied by the velocity of the electron in this orbit. So these are two quantities: circumference of the orbit, and other is the momentum of its orbital motion. So one condition that Niels Bohr gave, that the product of the circumference multiplied by the momentum in orbital motion should be equal to n integer, and let us call this integer as n, as we do often in algebra, multiplied by a constant, and that constant is called the Planck constant. The Planck constant had been found in the case of explanation to be given on another different item. That is, again, if we have to go into the history of the Planck constant, then we have to put the pause button once again and go back. Now that will take our story in a completely different direction, and we will lose the focus on atomic issues. Now what Planck had said, but I'll just give you very briefly two events with which this Planck constant is important, and it could enter into the atomic world, and that it could enter was understood by Niels Bohr. Now Planck had because, as you know, that when we heat an object, take a piece of iron, if I heat, you'll find that it is first turning red. We call it as the red hot. If you heat it further, you'll find that it develops a little bit of bluish tinge. Heat it further, you'll find that it is turning a little deeper, and finally a violetish tinge, and finally it becomes white. So how does this happen? This was an idea which people never understood. They never understood this idea until Max Planck in the year 1900 gave the hypothesis that light actually is absorbed or emitted in small amounts. It's not a continuous thing. We might see it that I'm heating continuously, but it is getting transferred. It transfers energy in small steps, as if you are throwing pebbles, as if uh, when you make rice, and we just take a cup, and we know that this much rice is needed. We put it. We never count the rice grains, do we? I don't know how many thousand or million rice grains we eat every day. Yes, we never count. But this rice that we are eating consists of rice grains. So energy, one way would be just take a cup and pour everything, and the other way could be that you pick up every rice grain and put in the pot. Correct? So it is the second way that light transfers itself, the energy, and that was understood by Max Planck in order to understand this phenomenon, that while heated objects first turn red, then bluish, and this amount that it transfers is called a light quantum. Light quantum. Quantum means a given quantity. It is not can be anything, right? It is a given quantity, and that is the idea of a quantum, that it is only possible in a given quantity. That is, and this given quantity will depend on the frequency of the light multiplied by a constant, which he put it the number small h letter. So h into nu, where nu is the frequency. So I can write E is equal to h into nu. Nu is the frequency of light, and H uh, is called the Planck constant. So everything has to be transferred as h nu, 2h nu, 3h nu. Then if four of them you transfer, 4h nu. If five such quanta transfer, 5h nu, and so on. And you can never have any transfer like h nu by 2 or h nu by 3 or h nu by 17. So it has to be always multiples of h nu. Okay, multiples of h nu. It has to go on. Now this was the idea first given by Planck, and with the help of this idea, we could explain the above phenomenon of how energy get transfers in the form of the way Planck said that heated objects would have these kind of colors, and colors, as you know, are determined by the frequency of the light. So once this is done, then Niels Bohr idea was, can we use this concept inside the atoms? If atoms have to absorb and transfer energy the way Planck has said in the form of quanta, the electron's motion should also be in the form of quanta. That it is not possible for it to have all possible orbits. There are only some given orbits that are possible. And that condition one has to explore. Niels Bohr gave that condition, that condition should be what I just now said. I'll repeat, because this is the cornerstone of atomic quantum science, that is circumference of the orbit multiplied by the momentum in the orbit should be an integer multiplied by Planck's constant. It cannot be half integer. It has to be 1 into h, 2 into h, 3 into h, 4 into h, and so on. So all the orbits that are possible inside have to satisfy this condition that the circumference multiplied by momentum should be n into h. So what happens that the motion inside the atom gets modified, that not all possible orbits are possible. Not any arbitrary dynamics is possible, but only those which satisfy. And these orbits should also satisfy another important condition, that the kinetic energy of the motion of the electron round should be such that it does not fall into the nucleus. This kinetic energy of motion should balance the potential energy of attraction towards the nucleus, because otherwise it would fall. This is one condition. And secondly, because of that, all the orbits that are uh, possible have to be defined by satisfying a second condition, and which was the Bohr condition I spoke just now. So it is a combination of these two which determine. So with all these, what happened? Could we explain that the time scales, what should be the time scales? And the great success of this theory of Bohr was that as a consequence of all these, by trying to put electron mass, electron charge, by trying to say that yes, they have to go in orbits, but the orbits have to satisfy that that centripetal repulsion away from the nucleus and the force of attraction towards the nucleus must balance each other, and they should satisfy this quantum condition. He could clearly show, because Planck's constant value was experimentally known, electron charge value was experimentally known, electron mass value was experimentally known. Exactly, this showed that the size of hydrogen atom should be 0.52 into 10 to the power minus 8 centimeters, which was known by other methods also, like, as I said, diffusion constant measurements. And what should be the time scales of these motion? When he tried all these things, they found that yes, time scales are also coming of the exactly of what are the atomic time scales are. So what a great success. And what a story. We don't know from where it began and how we arrived. We only know the final points. We know the destination. But in science, it is not the destination alone. It is the journey that is perhaps far more interesting than what you find you have arrived at destination. Now, from where did the journey begin? Did it begin with John Dalton? Or did it begin with Ernst Rutherford? Or did it begin with Planck? Or did it begin with electricity and magnetism? We cannot tell. You take away any one of them, you cannot arrive at what Niels Bohr had arrived at. And it gave us the correct time scales, correct length scales. And there are, of course, many other things that have been in between which are important, which I have skipped. And one of them should be photoelectric effect. And major contribution about understanding the photoelectric effect was given by Einstein. And Einstein's Nobel Prize was for photoelectric effect. And Einstein considered that photoelectric effect was his most profound work. So it was from the photoelectric effect that how energy can be exchanged between light quanta and electrons that finally led Bohr to come to that quantum condition. So we have reached our destination, but if you still ask me from where we should begin, I really do not know. Maybe there are various ways points where you can begin, and I don't think you can leave out anything to explain how we arrived at these. So we can stop here.
That was a really, really nice journey, like, and that you walked us through from beginning to end. I mean, I thoroughly enjoyed the journey and like all the, stopping points and how they arrived at the various conclusions. Any questions from anybody? I saw like some questions came through on the chat, and I think you did answer them. Any other questions? I don't think anybody has any questions, Professor. But do you think like we have other topics that we can cover within the quantum world itself next week, or
maybe one more, just one more, so that at the level of school children, we can know that yes, this is the point up to which you will be able to comprehend. And later things would be, you have to learn. As I said, science is a learning process. Okay. Yeah, just one more, because I will tell that the devices that we are using were not possible without knowing the quantum world.
Right. And I was going to say, I kind of wrote down like a lot of stuff that you were talking about, so I can type it up and send it out in the group. So you all can like look at it, and next time we will again have like a Q&A before we start. So like, we can just revise some of the things that we discussed today. Because we covered a lot of ground today.
Yeah, we would, next time we'll talk of the quantum world of materials.
Okay.
Why is a solid, a liquid, and then why is something a conductor, something not a conductor, and something is, and some objects. All of you are sitting in the Silicon Valley, yes,
Yeah.
And people call Bangalore as another Silicon Valley, correct?
Correct.
But we don't grow silicon here, do we?
No,
there's no silicon factory in Bangalore. No silicon factory. But why is it a Silicon Valley? So anyway, we will deal with materials, and I think we can close with that.
Okay.
Okay.
Yes. Sounds good.
Thank you.
Thank you so much, everyone.
The quantum world of materials. You can put that as title.
Yeah.
Okay.
Yeah, I will.
Thanks. Thanks.
Thank you.
Bye.
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 Bye. Bye. Bye. Thank all of you.
Yeah, thank you.
Bye.